Oh, hello there! My Unity Voxel engine is developing quickly. Today, we will be rendering infinite voxels yet again, but we will be using a level of detail system specially designed for ray tracing. I got the shaders from the last episode rendering in the scene editor for live updates. We can merge the existing scene camera with our custom camera to get a combination of two images. I got this free Skybox to enhance immersion. Any voxel drawn will overwrite the Skybox, like a painter layering dry acrylics on canvas. This image merge will be used in later episodes for particles. Merging helps to keep a shader pipeline modular and unlimited in flexibility. A common example of a modular shader is post-processing, or PP for short. Post-processing is any shader run on every pixel after the scene geometry is drawn. Common examples include bloom, anti-aliasing, deferred shading, lens flares, and distance blur. By adding a post-processing filter that shifts every pixel horizontally according to a sine wave function with time as an input, the screen will writhe like water. I pre-calculated this sphere with Perlin noise distortion. The sphere's distance function is ran on every voxel to determine solidity. It gives the illusion of a planet floating in space. Remember, we can use any function to determine voxel values. Minecraft-style generation is a wicked vice that need not be obeyed. This young man is named Chesmond. Though it may not seem so, this is arguably the most impressive achievement of theoretical computer science. To my knowledge, no engineer has implemented a Chesmond asteroid before. Therefore, I am ahead of my contemporaries by an order of magnitude. The block's changing size is my naive implementation of level of detail. The scene is a cube with exponential subdivisions. First, we calculate the highest detail scene. Then we recursively reduce sets of 8 blocks into one block. We repeat until we only have 8 gigantic blocks. I call this a dense voxel octree due to it being Octree shape, but it's really just baked in level of detail. One could even argue it's a 3D MIP map. And indeed it works identically in memory. Since all levels of detail are available in video memory, we can dynamically decide which voxel size to traverse. Each ray stores a distance value that represents how far from the camera it has traveled. We can change the grid we step across when arbitrary distance thresholds are reached. This helps to smooth the infamous popping in effect seen with rudimentary level of detail implementations, where a blobby mockup suddenly turns HD when approached. The black lines between voxel sizes was the problem with threshold detection, but I left it in for visual demonstration as it helps to delineate borders. The goal of detail changing is to reduce video memory usage and rendering time. This solution reduces rendering time, but actually increases video memory. Considering that ray tracing is known for blowing up computers, mayhaps a small sacrifice in memory is worth it while I design more efficient data structures. I have added texture support using a single 2D texture import. This is why only one texture is being used at a time. All the rainbow color variation is added in the shader. The eagle-eyed may notice the gray shadows and the edges between block faces. This is voxel space ambient occlusion, without any smoothing applied. Ambient occlusion is the imitation of shadows that form as a result of few light rays bouncing into smaller spaces. If you need an example, look at the point where your walls meet each other, or where the ceiling meets the wall. Ambient occlusion is hugely necessary for Minecraft-style lighting, as it is the only indication to the eye of depth changing. Voxel space here just means the shadows are determined by counting the 8 voxels adjacent to a ray hit position to determine approximate shadow contribution. The final trick here is ray distortion. Each ray has an unchanging direction vector. By rotating the direction every time we advance one block, we simulate a spiral pattern. There are all sorts of ray distortions we can iterate with. Instead of distorting the world, we apply the inverse distortion to the rays. We are changing the way light travels before hitting the imaginary eye. Imagine a ray coiling around before flipping back on itself. Mind-bending stuff. Minecraft's infamous acid shaders use a similar concept. I created a separate demonstration of how the ray can change the direction over time. you can see the original direction bends to the right as time passes. Oh, it looks like the ray got feisty. By adding zesty rotation functions, this approach plots emergent 3D shapes. Each time a block is created, that symbolizes the block position being sampled for solidity in the real shader. At one point in testing the main engine, I was confused why the far-off objects weren't being rendered. I then realized the ray was vibrating around a single point like a yo-yo. It had slowed down so much it was just bouncing around in place and terminating its journey. Graphics programming is a cat-and-mouse game, where the cat is you and the mouse is an esoteric, conceptual, emergent behavior beyond your comprehension. Next episode, we will experiment with Octree compression, multiple textures, reflections, and smooth shadows. See you then!